Hi, my name is Louis, and I'm going to present a joint work with Guillaume Baudard, Eric Atkinson, Ben Sherman, Marc Pouzet, and Michael Carbin. In our paper, we propose a language dedicated to the programming of reactive systems with uncertainty. The particularity of the language is that it allows the combination of deterministic and probabilistic reactive components. It can be useful to program an application like the SLAM, where a robot must infer its current position on the map of its environment. Let's run a live demo. So I can control the robot, which is represented with a green circle. The grayscale represents the estimated color of the map. The red circles represent the estimated distribution of position. And the white circle is the reading of a color sensor that is a noisy sensor, meaning that the robot can be on the black cell and it can, for example, read white. The wheels of the robot are slippery. So when I ask to go left, the robot can move, but it can also stay at the same position. It makes the tracking of the position challenging. I can launch an automatic mode. In this mode, a deterministic controller has a feedback loop with the probabilistic component, which is in charge of inferring the map and estimates the position. We call that inference in the loop. Thanks to the probabilistic programming approach, we have overt uncertainty, meaning that the robot can decide to stop to explore the map when it is confident enough that it has discovered the right map. So let's fast forward. Now that we have inferred the right map, we can go back to the talk. So I'm going to present the language and its semantics, show how we can do inference on infinite stream of data using bounded resources, and present some evaluation results. The language is built as an extension of a synchronous data flow language, which is a state-of-the-art technology to program embedded systems. Consider here the example of a robot equipped with an accelerometer on the GPS. It receives a stream of acceleration and some sporadic emission of the position. So this robot can be programmed by the parallel composition of two stream processors that we are going to program in our language by writing two mutually recursive equations. But in practice, the accelerometer on the GPS provide noisy information. So to deal with this uncertainty, we are going to use probabilistic programming. So we have defined a language called ProfZelos that extends the synchronous data flow language with probabilistic construct. It allows the composition of deterministic and probabilistic components and is doing inference on stream of data. So let's see how to program our tracker. It is going to use the classic probabilistic programming construct, which are sample to introduce a new random variable and observe that is conditioning the probabilistic model. The graphical model of the tracker is the following. The white circle represents latent variables, which are random variables that we want to infer, so here the state of the robot, and the gray circles are variables that we observe, so here the acceleration and the position. To program this system, we are going to define the stream of state x as the sampling in a Gaussian distribution centered on the previous state. Then we condition the model using the observation of the acceleration, saying that the acceleration component of the state should be close to the observed acceleration. Similarly, we can further constrain the system with the position when it is available on the GPS. We are doing that using the temporal control structure of the language. So the semantics of the language is a semantic of streams, where a stream is a pair of an initial state and a transition function. And the transition function takes an input state, then is going to output a new state for the next iteration and the value for the stream. So let's see that on an example. If we consider the constant 1, it has the trivial state unit that is not modified by the transition function, and at each iteration is going to output the constant 1. If we consider now the more interesting operator, which is the unit delay, pre of an expression E, the state of this expression is going to be a pair composed of the state of E and the value of the expression at the previous instant. So let's see how this works on an example. If we compose our constant 1 with the pre-operator in the equation x equal 1 plus pre of x, and the initial state is the pair unit 0, then the output is going to be 1, 2, 3, 4, and so on. So if we simplify the circuits and start from the state unit 0, we're first going to split the state between the state of the constant 1 and the previous value of the equation. Then we can perform the addition, which then going to output the value of the stream 1 and build the state composed of the unit value and 1, that is the input for the next iteration. Now, how do we go from deterministic to probabilistic streams? We saw that a deterministic stream is returning a pair of a state and a value. The idea of a probabilistic stream is that instead of returning a pair of state value, is going to return a measure over that. So what is a measure? A measure is a function that associates a score to a set of possible outputs. And from a measure, we can build a probability distribution by normalization, which means that if we have a measure applied to the set of all possible outputs, it should return 1. Let's see a few examples. If we have a Bernoulli distribution, which corresponds to a Bayes coin, here of parameter 0.3, and we ask what is the probability to get the value 1, then it's going to return 0.3. But if we ask what is the probability to have 0 or 1, then it's going to be 1. Now, similarly, if we have a normal distribution centered on 0 with variance 1, and we ask what is the probability to be in the interval minus infinity 0, then it's going to return 0.5. Another measure that we are going to use to define the semantics of the language is the Dirac delta measure. So the Dirac of x is going to be 1 if the set of possible output contain x. Otherwise, it's going to return 0. So how do we define the semantics of our probabilistic streams? So we can see one of the fundamental operations, which is that we can lift any deterministic expression to a probabilistic one. If we have an expression E, we evaluate it on an input state S, is going to return the pair state value that we are going to build the Dirac measure of this pair. Now, the key operator of probabilistic programming is the inference. So it allows to make the connection between probabilistic expression and deterministic one. This expression takes as input a probability distribution of states. Then it's going to integrate the measure defined by the probabilistic expression E over all the possible states. This is going to define a new measure mu that we are normalizing to get a probability distribution over the pair of state output value. Then we can split this distribution into two marginal distributions, the distribution of state and the distribution of values. For the implementation, the main challenge is to compute this integral. So a classic technique is a Monte Carlo method called particle filtering, where the idea is to execute multiple instances of the expression E to build a distribution of the possible outcome. So how does it work? On our example of the tracker, simplified to one dimension. At time step t0, we're first going to sample a value from the Gaussian 0, 10. So with the particle filter, we will have n particles actually drawing values in this distribution. These are some possible value for the random variable x. Then the observe statement is going to condition this sample, saying that the one closer to the observed value are going to have a higher score than the other one. Then, to go to the next step, we first update the state, saying that pre of x is the value of x at the previous instant. Then we can sample from a Gaussian centered around the previous random variable. This gives us a new set of samples that we can condition again with the observe statement. And it goes on like that. So a main benefit of this approach is that it is by construction executed in bounded memory. But sometimes the accuracy of this method is very poor. So we also have implemented an extension of the particle filter that is called delay sampling. The idea of this method is that each particle can perform some symbolic computation to improve the accuracy of the inference. So on our example, at time step t0, when we sample from the Gaussian, what we are going to do is not to draw some samples, but construct the Bayesian network corresponding to the system. So here we are creating a node in the Bayesian network, which is a random variable, normal 0, 10. Then, when we do an observe, we first introduce a new random variable, the Gaussian, which depends on the variable x, represented by the arrow in the graph. And the observation is going to condition this random variable with the values 3. We propagate this information then to the parent node. At the next time step, we first update the state, then create a new random variable which depends on the one of the previous instant. And similarly, the observation creates a new random variable, condition this variable, propagate the information. And it goes on like that. So this method can be even exact in some cases, but to implement it, a naive way is going to create pointers to all the nodes in the graph. And so it's going to lead to some memory leaks. So here we can see on the gray line that the longer we execute the program, the more we consume memory. So we have designed an extension of the delayed sampling algorithm that we call streaming delayed sampling that is going to be executed in constant memory. The main idea is that we can reorder some operation on the graph such that we can get rid of some of the pointers. That way, we can erase some of the nodes that will have no effect on the current state of the program. And that way, the inference can be executed in bounded memory on a large class of models. To evaluate the inference, we have built a set of examples that exercise a set of language features, which are the moving parameters, like the random variables in the tracker, but also fixed parameters, like the map in the SLAM example, and inference in the loop. So we compare the two algorithms that I've just presented, and we can see that when we increase the number of particles, the loss is decreasing, meaning that the inference is more accurate. But naturally, if we do inference with more particles, the execution time is going to be higher. So here we can see different trade-offs between the particle filter and delayed sampling. it's much faster to execute one particle with the particle filter than it is with the streaming delayed sampling. But the SDS is more accurate. So how to compare that more formally? So we set as a baseline the accuracy of streaming delayed sampling with 1,000 particles. And we look at how much time it takes for each algorithm to reach a similar accuracy. So this figure is a sum up of the results. We can see that in all the cases, the streaming delayed sampling algorithm is much faster, and it is due to the fact that it requires much less particles. And in some cases, it only requires one particle because the inference is exact. And in some cases, like for the SLAM, the particle filter were not able to reach an accuracy similar to the streaming delayed sampling algorithm in a reasonable amount of time. So thank you for your attention, and we are going to be here to answer your questions.